Hello, friends. Welcome again for the Turbulence seminar. And this week's speaker is uh, Professor Pablo Mininni, and he's a very well-known name in Turbulence. Uh, so Pablo did his master's and PhD in Argentina, Buenos Aires, and then he went to do postdoc in NCAR with Anik Puke. And he spent several years in NCAR as a researcher. Then he came back to Argentina, the University of Buenos Aires, and he's a full professor in the University of Argentina, Buenos Aires. I may not get the university name right, but I know it's Buenos Aires. And he worked on many topics. He has a very nice code, and he has published a lot of very interesting papers. So Pablo today is going to talk about geophysical turbulence, geometry, topology, and dimensional reduction. Okay, Pablo, so please start.
Okay, so thank you very much. So thank you for the invitation. So it's nice to give a talk to your group. We were talking before the beginning of this seminar about I was planning to go eventually to India, and then the COVID situation started. So I hope eventually I should be able to visit you. But this is, I guess, a nice opportunity to talk about what our groups do in turbulence from different points of view. So I will talk about geometry, topology, and dimension reduction. And this is a very old problem in fluid dynamics. It has been approached from many different places. So I will try to convince you that there is still room to do interesting things when we talk about dimension reduction. So what I'm going to tell you has been done with a lot of people. And Nicolas Suchowolski was a former PhD student in our group. Sophia Angryman is currently a PhD student. She's working with experiments. I will talk a little bit about that. And then many collaborators in our university in France and in the US. So you can see the next slide, right?
Yes, I can see the slides. It's working.
Okay, so this is actually what you see in the picture is just roughly 2/3 of our group. So this picture you can see it was taken during COVID. So we had a group meeting, and 30% of the group was not there. So we have a rather large group that does turbulence with many applications. So part of our group works in space physics and plasma turbulence. Roughly 2/3 work on fluid dynamics and neutral fluid turbulence. So, and the idea in our group, we have this group, the idea is to mix theory, numerical simulations, and laboratory experiments. So we maintain several codes. So one if goes, most of the simulations I'm going to show you stem basically from simulations done with this code. This is just a traditional pseudospectral parallel code. We have a new code called Spectre, which is a code to do channel flows, Rayleigh-Bénard convection, and other flows, turbulent flows in which there are non-trivial, so non-periodic boundary conditions. And this is also a pseudospectral code. So we use a new method to do efficient fast Fourier transforms, keeping the spectral conversions when boundary conditions are non-periodic. We have codes to do dynamos in spheric containers. We have a lab, so I will show you a little bit about experiments. And we also have maintained collaborations with other groups to develop tools for data analysis. So we have worked for a long time helping with the development of vapor. So what's the story of geometry and topology? So the basic idea is in a turbulent flow, we have local properties, which are geometrical properties. So for example, when we look at the tracer and we have fluid element in some region of space, and we wonder how the fluid is in the vicinity, so how gradients are, whether we have a saddle point in the vicinity or not. That's a geometrical property. And then we have global properties of the flow, and that's topology. Or they may be properties of the phase space or the configuration space of the flow. So the idea of looking at geometry and topology either of the flow or the phase space is rather old. So probably the first attempt to try to reduce the dimensionality of turbulence to a few degrees of freedom, and then to look at properties of the phase space, come from Landau. So Landau had a model for how laminar flow goes through a series of bifurcations into a turbulent state. So this transition from laminar to turbulence, Landau had what we now call amplitude model. So very simple equations with just a few degrees of freedom for the amplitude of some modes. And then there is the famous Lorentz model for atmospheric convection. So Lorentz, I mean, I guess all of us know this, but actually Lorentz model was derived from Navier-Stokes. So Lorentz was working with Boussinesq for a stratified atmosphere. So he had an atmosphere that was stably stratified, and then you have the heavier fluid in the bottom, lighter fluid in the top, and he wanted to study the transition to convective rolls. So he basically truncated the Boussinesq equations to just 3 modes, sines and cosines, to try to get this convection. And basically X, Y, and Z in Lorentz models are just the amplitudes of these 3 modes. And Lorentz model is just a system with 3 degrees of freedom that has quadratic terms that are conservative, and that's not a coincidence because these terms are coming from the Navier-Stokes equation. So the structure of these terms is similar to the nonlinearity in Navier-Stokes, and then we have forcing, and we have a control parameter, which is R, which is the Rayleigh number that basically controls how stratified the atmosphere is. And what Lorentz found, much to his surprise, was that he had a stable solution, and he was expecting this. So as he increased the Rayleigh number, he went to a stable solution, to an unstable solution with a bifurcation, a pitchfork, with 2 new stable solutions. And that's what he sort of expected, to go from one state to another one. But then he kept increasing the control parameter, the Rayleigh number, and at some point you have a second bifurcation, you go through a Hopf bifurcation, and you go also from stable to unstable orbits, and you keep increasing, and eventually you reach a chaotic solution in which you have sensibility to the initial conditions. So basically you have complex solutions that emerge from very simple dynamical systems, and you have this exchange between local and global properties. Right? So global properties of phase space have a huge impact on the dynamical evolution you can get. And actually, concerning global properties, an important thing is that, and we know that in turbulence, are things like global invariance. So for example, even in the complexity we can get in the Lorentz attractor, all trajectories are bounded by an energy surface. So basically we have a system that is out of equilibrium, that is forced, that is dissipative, and the trajectories cannot go beyond the maximum in the energy. So there is a surface in phase space that bounds the trajectories. So if we try to tackle a problem like homogeneous and isotropic turbulence, things get nasty. So these are simulations that I did probably like 20 years ago. So we all know this. So you basically you have 1 control parameters for homogeneous and isotropic turbulence. You increase the Reynolds number, and you have a multi-scale process. So at any point, if you have questions or comments, please stop me. So the idea is, if you try to to build a model with a few degrees of freedom for this system, you are doomed. There is nothing that can be done. Or at least not for the completely homogeneous and isotropic case. If you have boundaries, or if you have conditions under which there are some structures that get a lot of the energy, then you can try to do a reduction like Lorentz did. By the way we solve these equations is the way we solve the equations numerically is very similar to what Ed Lorentz did, because what we are doing actually in a pseudospectral code is to do a Galerkin truncation. So we truncate the system to, in this case, many degrees of freedom, 10 to the 9 or 10 to the 10, and we just integrate all the equations. So what we want, at least to understand the physics of the problem, is to find ways to reduce the dimensionality of the system further. So if we go to geophysics, things get more complicated. So let's say we take the atmosphere. If we want to take a very simple problem of the dry atmosphere at night or of the ocean, what we have is a stably stratified flow. So we go back to, we have density fluctuations, we have the dense fluid in the bottom, light fluid in the top. A dry atmosphere, we can model, if we want a very simple model, with the Boussinesq equation. So basically we have the momentum equation for the velocity, we have buoyancy forces, and we have density fluctuations. Okay, so if we integrate numerically this equation, we get solutions like this. So let's take a look at the full box. So what you see here is this line is for n is the Brunt by Sala frequency, and it's proportional to the square root of the background density gradient. So the larger n, the more stratified the flow is. What you see here is a side, is a view from the side, and this is a view from the top of the density fluctuations. So for n equal, actually this is density fluctuations, and this is vertical velocity, sorry. So, so for n equal 4, we have a flow that is, let's say, weakly stratified. So you can see we have layers, but there is a strong mixing. We have these structures, we have all these vertical mixing, and we can recognize some Kelvin-Helmholtz billows and so on. We increase the level of stratification, we have thinner layers. Now the layers are better defined. It looks like we have less turbulence, but you can still recognize this mixing and the Kelvin-Helmholtz billows. By the way, what you see here is a zoom into exactly these structures. So now we have many control parameters. We have the Reynolds numbers, we have the Fruit number, we have Richardson, which are all associated with the level of stratification and how unstable the flow locally is to convection. Now we have waves, because now we have gravity waves. We can have internal gravity waves. If we perturb the system, fluid elements will oscillate around the equilibrium position. We have eddies. We have an isotropy. We have a preferred direction given by gravity. And we still have a huge number of degrees of freedom. So it looks like actually, when we try to go into geophysical flows, things get more complicated than in homogeneous and isotropic turbulence. However, I will try to convince you that actually some problems are easier to tackle as things get more complicated. So let me talk a little bit about the phenomenology and some properties of this kind of turbulence. So what you see here are measurements of temperature, vertical velocity, and horizontal velocity, so the winds, in what people call clear air turbulence. So this is exactly, you're flying on an airplane and suddenly you start to feel a bumpy ride where you're flying. So basically that's clear, you met clear air turbulence. So these are measurements, and you can actually see This is done actually on a flight over the Drake Passage. So you can see that you have regions in which the system is smooth. You can recognize their gravity waves. But you have regions in which all of a sudden you have huge fluctuations. And actually you have huge fluctuations in the vertical velocity. So that's clear turbulence. And you see that stably stratified turbulence has this property that it has smooth regions and regions in which suddenly it becomes very bumpy. This is another paper, recent paper in Physical Letters by Pearson and Fox-Kemper. And they took models for the ocean, so global models for the ocean circulation, and they show that this, what you see here, is dissipation rate. And dissipation rate is very intermittent, strongly localized, and non-Gaussian. And actually, if you take climatology statistics for the atmosphere, so this is the vertical velocity, and what you see here is skewness and kurtosis. White is the free, so Gaussian. And you can see that in most places we have red, so we have leptokurtic vertical velocity. So we have strong tails, so extreme events in the vertical velocity in the atmosphere. So going back to the DNSs, so we take, so this is in dimensionless units 2 pi, 2 pi, and here you're only seeing one layer. So this is a cubic box. We can also do elongated boxes, but this is just a cubic box, so the box keeps going. But this is just one layer. So if we, okay, so I think, so if we look at the time evolution, you can see it's smooth. What you see here is vertical velocity. Suddenly, turbulence develops. We have extreme events in the vertical velocity, several sigmas, and then it gets smooth again. There is another layer on top of this that may remain sort of, let's say, laminar. And basically, that's what happens. So you have sort of laminar ordered flow, some instabilities trigger, the flow becomes very, very rough. And then after several turnover times, it goes back to a well stratified regime and so on. Okay. So basically we have this transition between these two solutions. One solution that is stably stratified, well stratified with horizontal winds, and another one in which we have a lot of vertical mixing. So if, for example, we look at a fluid element, we will see we have, just like in the clearer turbulence data I was showing you, we have these wavy solutions, then we have mixing, and then we go back to wavy solutions. So if we look at the statistics, we have leptokurtic events. And I want to be, I want to emphasize something that it's, from my point of view, surprising for this kind of turbulence. We are used to find extreme events in field gradients. So here what you see are vertical gradients, so the vertical derivative of the vertical velocity and of density fluctuations. And we are well used in turbulence to have these strong tails, so a large probability, larger than Gaussian, of having extreme events. And we know that if we do structure functions, velocity increments, and so on, the smaller the scale we look at, the stronger the tails we will see. But what we have in this case of turbulence is we also have extreme events, so non-Gaussian statistics, in the actual fields. So what you see here are PDFs of vertical velocity and density fluctuations. And depending on the Brun-Väisälä frequency, so depending on how stratified the flow is, we can have strong tails or not so strong tails. It gets more interesting. So here I'm talking in terms of the Froude number. So basically, smaller Froude number means more stratified. Fruit number close to 1 is we are getting closer to homogeneous and isotropic turbulence. So in the homogeneous and isotropic or more isotropic case, we have Gaussian statistics. In the strongly stratified case, we recover almost Gaussian statistics. In between, we have these strong tails that are non-steady. So you see the red PDF is a time average. What you see in all the gray dot curves is the time evolution. So we have these strong tails that actually flap a lot. And here you look at the kurtosis as a function of time, and you see that kurtosis goes up and down as a function of time. So let's try to build low dimensional models for this kind of systems. So I will start with the simplest possible model. It will be very,
Pablo,
yeah.
Can I ask you a question? Just go back to the previous slide.
Yes.
Here for 0.03, we don't have any, we do not have a long tails, or you do not, right? That is because it's making more 2D kind of, rather more well, what is it called? Stabilized flow? Stratified? I see. Okay.
Yeah, so in this direction, we are getting in the limit of homogeneous and isotropic turbulence, in which we expect small scale intermittency. So the small scales should be non-Gaussian, but the large scales are expected to be Gaussian. So when you look at the actual fields without computing any increment or gradient, you should see Gaussianity. And in this direction, we are becoming very, very strongly stratified. So yes, then you have layers that are well defined. And yeah, this is like, you can think of it as 2D layers. So that may be, that can be one way to see why we should recover Gaussianity in this direction. Now here we are in between, and the system is strongly non-Gaussian. Okay.
So do you have spectrum? I'm just wondering, did you plot the spectrum?
Okay, so the spectrum, so here the spectrum is -5/3. Here the spectrum is, depending on what quantity you look at, -2 or -3. And here, actually, if you look at the time evolution, the fluctuation, the spectrum also flaps. So when you have extreme events, it becomes closer to -5/3, and when you don't, it becomes steeper. So the spectrum is also, it can be also non-steady.
I see. Okay, please continue.
So I will actually show you why we should expect this behavior to happen. But before we go to precise model for these kind of events, let's start with a simple toy model. So, so let's try to build a simple toy model for the leptokurtic events. So basically, I will start with Boussinesq, and I will do a 1D reduction. So I will only keep the vertical velocity. So I'm using the convention used in atmospheric sciences. So W is the vertical velocity. So I only keep vertical derivatives, only vertical velocities. So this becomes a 1D equation. I will drop the pressure derivative. I will drop viscosity and diffusion. Okay, so I will write increments as doing a Taylor expansion, just as some length scale times the derivative. And I will go into a Lagrangian formulation. So d dt will be the partial derivative plus u dot grad. So basically what I will be doing is, okay, there we are. So basically what I will be doing is we will start following fluid elements as time evolves. So we will get ODEs that, unlike Lorentz model, in which we truncate in a Galerkin way for global modes, and we'll get ODEs that will be valid if we move along the trajectory of fluid elements. So if we do that, we get, with a lot of approximations, we get this very simple model in just 2 degrees of freedom for vertical velocity and vertical differences of density fluctuations, in which we have a linear term. So these linear terms just are associated with the gravity waves. We'll have oscillations, and then we'll have nonlinear amplification of gradients. So we can put back, just to regularize the system, we can parameterize some damping associated with the viscous damping, and we can add some forcing. And if we integrate numerically just this set of 2 ODs, something very funny happens. So what you see here in blue is the kurtosis as a function of the Froude number. So here we have large Froude, so here we're in the limit of heat. Here we are very strongly in this limit, we are strongly stratified. And these are DNSs in blue. So, and you see what I was showing you before, we get a kurtosis of 3, so Gaussian statistics for the vertical velocity in this limit, Gaussian statistics in this limit, and this huge peak with a lot of extreme events for Froude numbers around 0.1. And if we do an ensemble of runs of the ODEs, this toy model can actually reproduce this behavior. So actually what happens is, this is a sort of stochastic resonance in which the waves get non-linearly amplified by the stretching, so by the non-linearities in the system. So it's a lot of fun that just a simple model can reproduce what we get in the DNS. And actually, this has an impact on mixing, right? Because when we have these extreme events, we also get a lot of vertical mixing, and this is important for the atmosphere and the ocean, and actually that can be measured in many different ways. Now, this is just a toy model. So my question is whether we can do in a more formal way, and whether we can identify properties of the underlying phase space, global properties of the underlying phase space of a Business system and of turbulence from a more detailed derivation of a reduced model. So let's do a careful dimension reduction of the system. So to that end, basically what I will work with field gradients. So we have the tensor of the velocity gradient, and we have the density fluctuations gradient. So from this quantity, we can build 7 scalars. So one is just the trace of the square of this tensor. The other one, R, is the trace of the cube of this tensor. The flow is incompressible, so the trace of this tensor has to be 0. And then we can build combinations of these tensors that are scalars. And of course, we have some that involve the vertical direction, because remember, we expect the system to be axisymmetric because we have gravity, so we have a preferred direction. So with these 7 quantities, we can go back to the Euler equations and formally derive this closed system for the field gradients in a Lagrangian framework. So this time derivative follows fluid elements. Here I'm doing a couple of simplifications. So again, I'm dropping viscosity, so no viscosity, and I'm dropping a part of the pressure Hessian. Now, something interesting is if n is equal to 0, so we have no stratification, we recover a very famous model for velocity field gradients, which is the Bill-Foss model, or the QR model, or Charles Menneveau has worked a lot on this problem, and these models are also sometimes called delta V models, depending on how you write them. But basically, this is a model for vortex stretching and amplification of shear in the homogeneous and isotropic case, so n equal to 0, it explains the local formation of structures in the Euler equation up to a point, because it also has a finite time singularity. So it has solutions that run away. And the reason why that happens is because we are dropping viscosity and we are dropping part of the pressure Hessian. Now, when n is not 0, gravity waves up to some level regularize this system. So this is really nice. You can integrate these 7 ODEs, and if amplitudes, if you don't push the system too far, you don't have solutions that run away. Okay, so this looks like a mess. Actually, it's not a mess, right? Because we started with a system that has 10 to the 20, 10 to the 30 degrees of freedom, and we end up with a set of ODEs with only 7 degrees of freedom. I will try to convince you that there is still physics and relevant information here, even though we did a brutal truncation. So let's first of all discuss whether there is physics in this mess or not. So if we take, for example, one of these equations, just the last one, and if we go back into the actual fields, so remember, for example, S is the vertical derivative of density fluctuations, and we put all quantities back, actually what we have is an equation for the Lagrangian evolution of vertical gradients of density fluctuations. And actually you can go back to the DNSs and you can check that actually this quantity evolves in time as expected. So if these terms can act as sources, and if you have gradients in certain directions, then you will have an increase in the vertical gradient of density fluctuations and so on. And another interesting thing is that when n is equal to s, which basically means that the vertical derivative of the fluctuations becomes equal to the background density, these terms goes away. So basically what happens then is that the vertical derivatives of the gradients, of the vertical derivative of the fluctuations in the density can be amplified until they equal the background density gradient. Once that happens, basically you're erasing the background stratification, right? So you have a stratified flow, and if this quantity grows, you have fluctuations that are so large that locally you are not stratified, and then you will have convection. And that's why you can amplify this term until you reach that point. So, and this will have an important impact on the dynamics. So let's go back to the system with 7 degrees of freedom. So we can look, now we have a set of ODEs, so we can do nonlinear dynamics, we can look at fixed points. The system has 2 fixed points. One is all the gradients equal to 0, so this is a stably stratified flow at rest. If we perturb the system around it, we will actually get a manifold, an invariant manifold, in the surrounding, which corresponds to, no, it's this one, which corresponds to waves. So we have a stably stratified fluid at rest, we perturb it, we have oscillations. By the way, an invariant manifold is a manifold in phase space such that if we have an initial condition in that manifold, the ODEs will keep the evolution inside that manifold. Okay, so it's invariant to the time evolution. Then there are invariant manifolds in the vicinity of these fixed points. These are not relevant for the dynamics because they're very far away from where the action happens. But there is a global invariant manifold, this one, which actually it's global, so it's always there. It's non-linear. It's no matter how much you perturb it, it will remain there. And it corresponds to the example I was giving you before. So it corresponds to the vertical fluctuations of the density being equal to the vertical background gradient. Okay, so the case in which the fluctuations become so large that they overcome the background density and you are at the brink of the convective instability. So first of all, it's nice that we do a truncation of the full set of PDEs, and we get 2 fixed points and 2 invariant manifolds in the vicinity associated with physics that are relevant for the dynamics. Something that is even more surprising for me is if we go back to the full set of PDEs, so now we do a DNS at very large resolution, and we put particles and we follow those tracers, and we keep the history of how velocity gradients evolve, and we do the statistics of that. Actually, fluid elements prefer to be in this manifold. So what you see here are diagrams of phase space. Remember, this is a 7-dimensional phase space. But these are diagrams of phase space, and what you see in colors is not coming from the ODEs, it's coming from the PDEs. And this is the probability of finding fluid elements in a Boussinesq flow in the vicinity of the invariant manifold. So these plots are done in such a way that these diagonals are the invariant manifolds we identified. Then you can see that actually fluid elements prefer to be in the vicinity of the manifolds. And the arrows are not coming from the ODEs, they are coming from the PDEs. So they are coming from the full set of PDEs and the time evolution of the fluid elements. And you can see that actually fluid elements evolve in this reduced phase space in such a way that as they get close to invariant manifolds, the evolution becomes slow. So arrows become very small. So these are invariant manifolds that are slow. And what are physically these manifolds? These manifolds are waves and convection. So, I mean, this takes a lot of details, but the bottom line is we can identify from a reduced model the global topology of the phase space of stratified turbulence. And what we have is, we have one fixed point that corresponds to gravity waves with a local invariant manifold that corresponds to gravity waves. So if we perturb the system, we will get oscillations around this point. Now, any fluid element that gains too much energy will escape this manifold. This manifold has a finite size, and the size of the manifold is proportional to n. There are only 2 slow regions in phase space, so it will go fast, the fluid element, to the other manifold, and the other manifold is at the brink of the convective instability. So the fluid element will find convection, a lot of energy will be dissipated there, and we will go back to the other slow manifold. So actually we have the fluid elements going back and forth between these 2 solutions, and just this very simple underlying topology of the attractor behind stratified turbulence can explain a lot of what I showed you before of intermittency, very strong extreme events in the density fluctuations, in the temperature, and in the vertical velocity, and observations of marginal stability and criticality in stably stratified turbulence. Okay, so I think I have 15 more minutes, so let me show you where we're going next with this. And and this is not stably stratified. So after doing this, I started to wonder whether we can push these ideas further. So whether we can go back to homogeneous and isotropic turbulence and use these ideas of phase spaces, topology and geometry of the phase space, and dynamical systems for 3D homogeneous and isotropic turbulence. So here we cannot do such a clean dimensional reduction. So what I will try to do instead is to wonder whether we can turn actual 3D turbulence into a 3D phase space. So actually, let's say we have particles in a 3D turbulent flow. These are particles evolving with a set, basically evolving with Newton's equations. So few degrees of freedom, but they're following an underlying flow. So can we use ideas of dynamical systems to reconstruct not now the topology of the underlying attractor, but the actual topology of the underlying flow, of the 3D flow? So if we think in terms of turbulence, if we think in terms of topology, we have an important invariant for 3D Euler, which is Helicity. Okay, so in the case in which we have no dissipation in Navier-Stokes and no forcing, we conserve the energy and we conserve the helicity. Now, helicity is important because for two reasons. Helicity has a lot of applications in geophysics, for dynamo theory, so for the generations of magnetic fields in stars and in galaxies. But helicity is very hard to measure in the lab. And the reason for that is helicity is basically the global alignment between the velocity and the vorticity. So measuring this in a simulation is easy. Measuring this in the lab is almost impossible because you need to know the velocity and the vorticity at every point in a 3D space, and you need to then integrate that. Now, helicity from the topological point of view, Moffat showed that helicity is proportional to the number of links of vorticity field lines. So you have a vortex tangle like the one you see here on the side, and the number of links, so the helicity in the flow is proportional to the sine number of links. So let's say you have just two vortex rings, helicity is proportional to the circulation square times the number of links between these rings, okay? So let's go back to the idea of turning turbulence into some 3D phase space. So let's say what you see here is an actual experiment. So this is a von Karman experiment we have here in Buenos Aires. And you see in this case a big particle, so it can be easily seen. And you can see actually that the particle wanders around just basically following. You can see that particle time to time gets trapped by some fluid structure or by the propellers, and it just moves. And let's say we can record, and actually we can do that with particle tracking velocimetry. Let's say we can track the trajectory of several particles. So then we will see that, for example, the particle does some loop, and we may wonder, is this loop associated with helicity in the flow? And there is a theorem that tells us, okay, for sure what we can do if we have projections of the trajectories is we can know the number of actual crossings of trajectories by counting the number of crossings in projections of the trajectory. So let's say we have 3D trajectories, we do a projection into a plane, and we do that into several planes. In each plane, we will have something like this, and we can count the number of crossings we have, assigning signs depending on how the crossings are. And the total number of actual crossings in all the trajectories of the particles will be just the average of the crossings we count in each crossing. Okay, so we can measure crossings of particles in a 3D flow. So are those crossings associated with the topological complexity of the underlying flow? So to do that, what we did was we took two experiments, the von Karman flow in Buenos Aires and the LEM experiment in Lyon. The von Karman flow can be compared with Taylor-Green simulations. They have similar geometrical properties. LEM is a homogeneous and isotropic turbulence experiment, so we can compare it with DNSs of heat. And actually we can record, now this is more like an actual experiment, this is not a measurement, but then we put many tracers and we do particle tracking velocimetry, in the DNSs. So in the simulations, what we do is we put millions of particles, and then we can do a scatter plot of number of crossings of the trajectories versus a dimensionless normalized helicity. And here you have experiments. So for example, this is for heat, the main plot. So here is the LEM, and all these are DNSs. So the LEM should have helicity equal to 0. The flow, because it's mirror symmetric, just because of the way it's forced. And all these other points are simulations up to 1,000 cubes. So these are like huge number of simulations. And you can see that K is proportional to H. So the number of crossings in the particle trajectories is proportional to the flow helicity. And the inset shows the same for von Karman and Taylor-Green. Many simulations, many realizations of the experiments. The number of crossings is proportional to the helicity, and the actual slope is the same for both experiments. For both flows. Okay, and it's the same independently of the boundary conditions, because the DNSs and the experiments have different boundary conditions. So it seems like, and we published this this year actually, so it seems like the number of crossings you get in particle trajectories is proportional to the topological complexity of the flow. And the constant that relates both is up to what we can say universal. So it doesn't depend on Reynolds number, it doesn't depend on the flow geometry, but it doesn't depend on the flow geometry, it doesn't depend on boundary conditions, it doesn't depend on the forcing mechanism. So this is like Alice looking through the looking glass, right? So Alice looks at the flow, at the actual flow, and it looks at the flow in the looking glass, and it can distinguish one from the other because she can distinguish right hand from left hand, that's basically the helicity, or she can distinguish positive crossings from negative crossings. Now, how this gets connected with dynamical systems? So we can go further, we can actually quantify what is the minimum time we need of measurements. So how long these trajectories must be to be able to identify the topology of the flow. You can see that if measurements are very short in time, we cannot distinguish flows with positive from negative helicity. All the error bars are one on top of the other, but as we increase the time, the length of the measurements, we can distinguish them. We can also measure what is the minimum number of particles we need, so how many trajectories we need to be able to distinguish flows that we are actually seeing or we are seeing through the looking glass. Now, this is important for machine learning, this is important for low dimensional systems, this is important for time series analysis and data embeddings. Why? Because basically, for example, when you do machine learning, you are doing exactly this. You have a huge data set, you are trying to reconstruct the underlying geometry and topology of if the system has evolution of an underlying attractor, or at least the configuration of a face of configuration space. And there is this question of how many points do I need for the neural network to be able to generalize. So this is fun, and this is fun because now we can use turbulence to actually measure in an experiment what is the minimum number of points we need to know the properties of the underlying attractor or of the underlying flow. So, conclusions. First, a very broad and general conclusion. And this is more of sort of philosophical conclusion. We often talk about the need for a general theory of turbulence, like the holy grail of our problem. And this has scared a lot of young students from working in turbulence all over the world, right? So turbulence is the last unsolved problem of classical physics. It's really nice, but we have been there for century, and we are still there. So then we may give the impression that turbulence is not moving forward. Now, if we go into actual applications and if we go into actual systems and we look at turbulence as an example of complex out of equilibrium systems, there are many, many things we can learn that are accessible and that can be useful for other areas of physics. So first conclusion. Then in a more particular way, so turbulence is actually a paradigmatic example of out of equilibrium systems. We can learn many, many things from turbulence, and we should, from my point of view, put the focus there. I think there are many, many nice things to say about applications, and when we go into geophysical flows or lab flows or industrial flows. So I think as a community, we should put more emphasis on that. So in many cases concerning this talk, local properties are the result of global topological properties, either of the flow or of the underlying phase space. So I gave you two examples. One is the large-scale intermittency of stably stratified turbulence. The other is the linking of particle trajectories. And just as a brief comment, we have topics that are related to this. So, for example, the preferential accumulation of heavy particles that plays an important role in cloud formation and in settling of particles is also another example of how the flow geometry affects transport properties. And I think Alex will give a seminar next week. So I have also been working with him on phase transitions in the particular case of quantum turbulence as dimensionality is changed. And that's another example in which dimensionality changes the invariant. So it changes the quantities that are conserved, and then you have a transition. So you have an impact in the actual flow dynamics. Okay, so thank you very much.
Okay, thanks, Pablo, for a very nice talk. Okay, so we are open for questions. Okay, so Alexandre has a question. Alexandre, I can unmute and please ask. Or okay, he's putting chat.
Okay.
Yeah, Alexandre, are you asking a question or in chat? Okay, let's see. I don't see your question.
I guess he may be typing. So.
Okay. He says, how do you measure helicity in experiments?
That's very good. So yeah, because that's actually, yeah, that's okay. So now we have a way to actually measure helicity in experiments. So in this paper we published in Physics Rev Letters, what we came up is actually with a way to calibrate. So now that we have this published, I would say the way to measure helicity in experiment is you do particle tracking. For you don't need a huge number of particles. So with typical numbers in an experiment, you do particle tracking, you count crossings, and that gives you a measurement of helicity. And I would say now it's the easiest way to get an actual measurement of the global helicity in the flow. So I have been working, I will tell you how we estimate for the experiments now, but before going there, so this is a question that I have had for a very, very long time. So working with Jean-Francois when he was doing, Pantong, when he was doing the dynamo experiment, one question everybody had was, is a von Karman flow helical or not? So now that's something that we can actually say. So what we did here, we did two things. So first we use DNSs, because there we can actually measure the actual volumetric helicity and we can measure the crossings. So most of the points here are from direct numerical simulations, and you do a scatter plot and you get the same slope. So that was good news. Then we got two experiments. So for the LEM, we know that it has to be non-helical because the LEM is mirror symmetric, it has 6 motors, and it's designed in such a way that no helicity should be injected on the average in the flow. So we basically assign helicity equal to 0 by construction to the lem, and then we computed the crossings, and we were happy to see that actually the number of mean crossings of the particles was equal to 0. For von Karman, what we did is we computed the crossings from the experiment also, and to estimate the helicity, we compared with DNSs of, so there are there are people that did actual von Karmans with penalty. So that gives you a first estimation of how helical the flow should be from a simulation. And we also took our DNSs of Kelvin Helmholtz, of Taylor Green, and we rescaled the helicity of this flow using PIV measurements to compensate for the differences between the poloidal and toroidal ratios of the velocities. So we used a little bit of geometry to rescale the helicity from one of these DNSs to compare with PIV of this flow to try to get a rough estimation of the helicity. So that's how you basically get this point. You see here, you can see that actually there are very huge error bars, and that's because we combined basically DNSs and PIV to try to get a rough estimate of the helicity in the von Karman. So, and we were also happy to see that the point was on top of all the numerical simulations. So that's how we got the experimental points there. Thank you.
So other questions? Okay, Rupak has a question. Rupak, unmute and ask, please.
Yeah, so this is a quick question. When you are experimentally measuring the multiple pressures or like multiple particles, so in simulation, I understand that each of the particles have an index. But in experiments, we do not have an index. So how do you track multiple particles simultaneously, especially when they're moving fast? I mean, like a fluid.
Okay, so I will. There is a question in the chat. I will answer that question later. Sure. So first, let's go to your question. So okay, so that's actually a problem that it's hard, but it has been solved. So there is a technique called particle tracking velocimetry.
Yeah, I mean, yeah.
So basically, what you do is let's go to just one particle, and then so you have to measure. So you have to illuminate your entire volume, right? So either you use a laser and you open it, or you use LEDs, but you have to illuminate your entire volume. And then you record these with fast cameras. You need at least 2, and 3 is better. So you use many cameras, and in each camera you have a different projection. Okay, and then you have a sequence of images at, let's say, 200 to 2000 frames per second, depending on how fast your flow is. And then basically what you do is you look at the sequences of images and you try to identify from all the different projections each particle. So you start with a guess, and you basically let time evolve, and you okay, so yeah, let's look at the movie again.
Yeah.
So let's say, so you have a guess of where the particle will move. So let's say you have a particle here. So, okay, so you have a particle here, and you know from the previous frame that it moved from there. So then you can do an estimation of where it will go in the next frame. And you look for a particle in the surroundings. And you do a guess that basically depends on the previous history and an assumption that particles should not have singular derivatives in the trajectories. Okay, so and then when you have many particles, that's what you do. You keep tracking them, and if they are in the same window because they get very close, looking at all the cameras, sometimes you realize, okay, for one projection they are very close, but in the other they are not. So you can distinguish them. And if you cannot, then you say, okay, so let's make a guess. Let's say this is actually particle 1, this is particle 2. And if in the next time they evolve like this and the evolution is smooth, then you say, okay, then I did the right guess. And if it's not, you swap them. And if in any of the guesses you get a sharp change in the trajectory or something that is not physical, then you discard that trajectory, right? So you basically measure 200 or 300 particles, and you may end up with 100 trajectories or 80 trajectories because you discard some because you cannot resolve. That's how it's done. So it's something that, I mean, you automatize, but it's painful. Yeah, but it's actually something that you can download code. We have our own code, but you can go to GitHub and you will find particle tracking velocimetry code.
Yeah, I work with PIVs, but like I was having this issue that think of two particles A and B, they are going towards each other. But after some time, like whether they have gone this way or they have gone this way. So how will you identify A and B? So if it is A is going here, B is going here, or A is going here, B is going here. Because we don't have an index for every particle in experiment. In simulation, we have that.
Exactly. Yeah, you don't. But that's what you do. So you basically keep the history and you try to make a guess of where the particles will be. If that fails, you go at whether the evolution is smooth or not. And if not, then and if it's not, then you stop the trajectories there. So you have trajectories. You always have in an experiment trajectories that start and end in time. So you say, okay, I can know where the particles are up to that point, and then I relabel them and I start new trajectories. Okay. Okay, so there is a question about, can we get a 7-dimensional ODE model for rotating turbulence? I guess so. So I don't know whether it will be 7-dimensional. It may be 5-dimensional because you have no temperature. But yes, my guess is there is a lot of potential in these kind of models. I mean, these kind of dimensional reductions were very successful in the 80s and 90s when Bill Foss introduced them, and Charles Ménéveau really pushed them for homogeneous and isotropic turbulence as a way to understand intermittency. But in the homogeneous and isotropic case, they have this problem that they run away. So they have runaway solutions. Now, when you have waves, it's nice because waves regularize the system. So we can do actually much more than just look at the intermittency in the stratified case. So for rotation and also for MHD, I guess cases with the preferred direction and with waves are good candidates to go back to these reduced models and see what happens. Yeah. So my guess is for rotating turbulence, it should be 5-dimensional.
All right. So I guess now it's my turn. He says thank you, Abhishek, to you. Okay, so can you go to the 7-mode model equation derivation? I just wanted to get a picture.
Yes.
Yeah.
This one.
So So these are real space derivatives. So you take the equation in the real space and you basically derive this dimension. So so I mean, this seems quite complex. How do you get, let's say, this R, the three terms, Aij, Ajk, Ki? So are you taking derivatives more and more times of the model equation?
It looks like a pain in the neck, but actually once you start to do it, it just goes. So so you start with dt, let's say dt ui.
Okay.
Right, so you have dt ui plus u shade d shade ui. So you apply and so on.
Okay.
So you apply the Shay,
I see.
and you start to do all the partial derivatives. So you just do all the math. So you end up for an equation for VT d Shay UI.
I got it. Yeah. So basically, you take derivatives, various derivatives.
Yeah,
and
but there is something. So there is a trick here, and that's why I was writing it. So when you expand this term, one of the terms is actually the advection of the gradient. So one of the terms actually goes into, this becomes the total derivative. And then the math becomes easier, because once you have the total derivative, then you got rid of one of the nonlinear terms, and then you can write all the rest as products of the gradients, and then you just keep taking derivatives, and you can reduce formally just the PDEs into these ODEs. Yeah, that's how it's done.
Okay, looks interesting. So Lorentz, he used Fourier space truncation. Galerkin, one person here, Pinaki Pal, and I also did quite a bit model building in Fourier space for thermal convection.
Yes.
And there's one paper on MHD. So similar things, has it been tried for stably stratified flows? In Fourier, well, like not real space like what you did here, which is interesting, but in Fourier space truncation of large scale modes. Has it been tried? I mean, I'm not, well, I didn't dig in for literature, but you may know. You understand my question?
Yeah, so in a way, Lorentz is actually, so Lorentz actually took the stably stratified problem, right? So he started with Boussinesq. So you can think that Ed Lorentz actually was the first to actually try to do a Fourier truncation. The problem with that is
no, that is the problem. That is for unstable stratified thermal convection.
Yeah, that's true. That's true.
That will be a different.
Yeah, that's true. So Lorentz is for unstable stratified, but it's the same set of equations. Actually, by the way, this set of equations is derived also from Boussinesq. So it doesn't matter whether it's stably stratified or not. What changes are the signs of n, right? So
that I agree. Yes. Okay.
So so the problem with that is if you truncate to, so yes, actually, so let's go in a historical way. So Lorentz actually did that, truncating by with just 3 degrees of freedom. The problem with Lorentz is it's very nice because he showed that actually there is all this complexity in just 3 degrees of freedom, and there is all this complexity in the atmosphere. But when you want to go into the actual physical system, the modes he picked are unstable, so you never see them in nature.
So I can tell you that a little bit about that part of the history. We did that kind of thing for large Prandtl number. In fact, his model does not work in experiments, numerical experiments. DNS, we compared with DNS. And his model, in fact, there is a pitchfork. Sorry, not pitchfork. Hoff is inverse Hoff. And in real thing is forward Hoff. So we have a 7-mode model. In my book, I wrote the 7-mode model. And then Pinaki has done a 13-mode model for 0 Prandtl number. We had 30-mode model too. The Pankaj Mishra is there in this audience. Probably you know Pankaj. So we created all this stuff for that matches with DNS. So that was the beauty of this. So it was DNS was matching with it. So I mean, I was just wonder whether stably stratified too, because it's a lot of stratification, no? So it means that there's a KZ mode. KZ mode is dominant KZ mode. And we can take that KZ mode and put some more. And that's why spectrum may be useful guide to see how many modes are relevant. So all that.
So someone that is trying to do that is Keith Julian in Colorado, in the US. So Keith Julian has been working, I think, with Knobloch on systematic reductions, and those work very well for the limit of very strongly stratified or very strongly rotating. So these are like these are asymptotic reductions in the sense that you take a few modes, but you do an asymptotic reduction so they work in a limit. Yeah, and I think he's getting in those limits similar results in the sense that you have this system jumping from one state to the other. What is nice of this Lagrangian reduction is that there is no assumption of the stratification being too strong. So actually this model works well for this case, right? So the case in which you have a fruit number in between. It's the system is not in the limit of very strongly stratified, it's not isotropic and homogeneous, and this model can capture these kind of transitions. But yeah, but that you can attempt going into this problem from the Galerkin point of view truncation. Yeah, and I would say for that I would check what Keith Julian is doing.
I see. There's one last question I will ask before we close. Is for fruit number order 1. In fact, I think we had fruit number probably 10. The spectrum we got was minus 11/5, Bulgio-Nabokov. That's what is expected. And I just wonder whether why are, I mean, you said it's 5/3, but I believe it should be 11/5 for fruit order 1. When it is nonlinearity matching the buoyancy.
Okay, yeah, I see. No, so what I mean, okay, so if that wasn't clear, what I mean is in the limit in which you recover homogeneous and isotropic turbulence, it should be minus 5/3. So for very, very, so yeah, so this is for fruit very, very large. Okay. So
yes,
very, very large.
That is
now,
Richardson 0, yes, okay. That I
yeah,
agree.
So yes, so for intermediate values, yeah, you may have a full zoology of different slopes. I haven't explored that, so
so we did this, so we have it in 2014, the 11/5 with 1,000 cube simulation. I mean, it is not a great thing, but that's 11/5 we kind of argued, and we're trying to do shell model. It's quite hard to get dual scaling like Bulgio-Nabokov thing, but the shell model, there's a student of mine, he's doing it right now. But yeah, so I think we can close. So if there's no other question, we can close.
There is a question in the chat.
Okay.
Yeah, Andres is asking about weather forecasting. So yes, this is rather new. So there is an interesting story about that. So people have observed in the atmosphere these extreme events, and they have discarded for a long time because they thought in many cases that they were problems in the probes, because it's weird to have non-Gaussianity in the actual fields. People are used to have non-Gaussianity in the gradients, but to have non-Gaussian events in the actual fields is strange. So so for long times, people have discarded these, and now that it's being seen in simulations and in models, people are going back to it. So I know at least of some people in Italy that are looking at an event called, there are boras in the upper atmosphere, so like holes, extreme events in which you have huge updrafts or downdrafts. So they're looking back at those problems to see whether they're an example of this. There is a recent paper on that. People in clear air turbulence in the National Weather Service in Argentina are actually also looking at whether clear air turbulence is an example of these extreme events. And I know people also in France that are looking at the oceanic problems to see whether there are some extreme events are example of this kind of behavior. So this is rather new. Yes, they could be used for low dimensional models for weather forecasting are used, for example, for something called nowcasts. So for very short time predictions. So in principle, yes, they could be used, but this is new, okay?
All right. So I think we can close the session now.
Yep.
So thanks, Pablo, for.
Thank
Thanks,
you.
Pablo. Yeah, thanks.
Yeah, and thank you also, Mahendra. It was a pleasure. It was really, really nice.
Yeah, great. We could meet at least virtually. Great. So
Yeah.
thanks, everyone.